So this question is asking you to determine the compound formula and Lewis structure of the following elements. So we were given potassium and sulfur here in this example that we did in class. And so when we're determining the compound formula, the first thing that we want to go back to is that periodic table and look at the valence, the charges based on the valence shell. So when we've talked about the valence shell, that is the number of electrons in that last orbit of our element. So, and that's what makes them chemically reactive. So potassium is in group family number 1, so it has a positive 1 charge, and sulfur is in group number 6, and it has a negative 2 charge. So unless we're telling you in a final exam or a quiz that you're dealing with a polyatomic ion, when an ion has a charge to it, okay, then we would have to tell you that there's an ion charge, because that would indicate how you would be able to determine your compound formula. So just keeping that in mind. So if you don't see anything like that, you can assume that your compound formula will actually be neutral, which to us in chemistry means we have a 0 charge. Okay? So what we're doing here is we're looking at our numbers, our valence numbers here, and we're determining how, what we need to do to each element in order to get 0. Okay, so the name of the game is 0. So right now we have a positive 1 and we're adding negative 2 to it. Okay, so when we're looking at our charges here, we're going to focus on the biggest charge, which is that negative 2, and ask ourselves, well, how can we neutralize that? So looking at potassium, each potassium element has a positive 1 charge to it. So if we actually add 2 potassium ions, so plus 1 minus 2, plus 1 gives us positive 2, and we still have that minus 2, and that gives us a charge of 0. So our compound formula is K2, or not K2O, I'm sorry for that. It is K2S. So essentially it takes 2 potassium elements to neutralize 1 sulfur element to give us a charge of 0. Sometimes it doesn't work out as easily, so like if we're dealing with other elements, like if we have charges of positive 3 and negative 2, for instance, then, there's going to be a little bit more work involved. Another, in terms of your factors in multiplication, because it's really really we want to get our math numbers to be 0. Another easy approach to this is when you're given your charge numbers, okay, so you have a positive 1 and a negative 2, you can just crisscross your charges to get the correct number. So we have positive 1 with sulfur, so we're going to actually give that, positive 1 with potassium, and we're going to give that to sulfur. And we have a negative 2 on sulfur, and we're going to give that to potassium to give us K2S. So it's not that we're crisscrossing the charges, we're crisscrossing the number of what the charge is given to us, so just to neutralize it. So that's another quick method to determine if you're on the right track. So now we've determined the compound formula, and now we need to move to the Lewis structure. So in a situation like this, when you're given a compound that's K2S, or that there is only one element present, yes, we have 2 potassium elements present here, but we only have 1 sulfur element, what we're going to do is we're going to write the generic formula down first, and that generic formula is going to be KSK. So again, if you're given, because we're using the example K2S here, because there's only 1 sulfur, typically that will be your central atom. It's not always the case, but typically the fewest number of elements that you have in a compound, that element will be your central atom. So for instance, aluminum oxide, which is Al2O3, Al2 will be your central atom. Okay, and then you have oxygens along the sides. But that's just a different example moving forward with this. So as with practice, you'll understand, it'll become a little bit more secondhand to you. So getting back to this example here, I'm now going to determine the Lewis structure. So those are those dots, okay, that we've been talking about that specifically focus on that valence shell, because it's that shell alone that creates the reactions and decompositions that we see happening in the lab and in our lessons. So what I'm going to do first off is I'm going to determine the number. I'm just going to draw in the number of electrons we have for each element. So potassium each has 1 electron in that valence shell, and sulfur has 6. Okay, so with this now, it is important that with the formula that you're understanding whether it might be a covalent, so sharing bonds, or it's just an ionic bond. Ionic bonds are always metals forming with non-metals. So when we look at the periodic table, okay, to determine if we actually need to maybe consider covalency, what we're doing here is we're looking to see if we're having a metal bind with a non-metal. And true enough, here in this example, potassium is a metal and sulfur is a non-metal. So we are actually dealing with an ionic bond. So potassium here, so again, we want to use that octet rule, which means that each element wants to have 8 electrons in its outer shell. How we get to 8 electrons in its outer shell can be either we're taking in electrons or we're giving away electrons, and that's important to remember. Because potassium has a positive 1 charge, it means that it's easier for it to give away that one little electron in its outer shell to be a whole 8 in the next shell below it. And it's easier for sulfur to take in 2 electrons to get up to 8. So either way, we are satisfying that octet rule, but it is important to remember that you're not always adding electrons. Some elements some families in our periodic table would happily give away up to 3 electrons, sometimes 4 electrons, to become neutral. Okay, so in this example here, what we're doing is we recognize, hey, potassium has 1 electron each, and they'd be happy to give that away because they're a positive 1 charge. Remember, electrons are negative, so we want to, when they give away that one negative thing, they become more positive. Sulfur, on the other hand, has 6 electrons. It only needs 2 more to be happy to be stable. So what we have here is an excellent sharing or giving away of electrons, which is our ionic bond. So potassium comes in to sulfur and says, you know what, I can give you my electron, I don't need it, I don't want it, and you can have 1 more. So sulfur now has 7 electrons. Another potassium comes in, has the same approach. Hey, you need 1 more electron now? I have 1 to give, so I'm actually going to give you that electron. So in terms of a Lewis structure, essentially what we're seeing here is we would have a K single bonded with a S, single bonded with another K. And I mean, you can fill in the sulfur bonds or the electrons if you want to, but in this situation it's not necessary, because when you don't see any electrons or dots in our Lewis structure, it's assumed that we have now completed, in its final form, we have now satisfied that octet rule, okay? It is important to show, though, the bonds, okay? So 1 line to us indicates 2 electrons, so that we know that sulfur has been satisfied with our octet rule. We know that potassium's been satisfied because it did give away that electron. So it has moved it over to sulfur so that sulfur was happy. So this would be your final representation of your Lewis structure.